Good morning everyone. Today we are going to see about advanced separation processes. So, the subsequent two classes also closely related to advanced separation processes. So, today we are going to see about the fundamentals of separation processes and what are all the advanced separation processes. So, in which we are going to concentrate on membrane separation processes. In subsequent lectures, we will be seeing what are all the major membrane separation processes and what their use in food industry and for food processing. So, it is a alternative to thermal processing, but though the course is about thermal processing of foods. So, we have also seen other non-thermal technologies in few lectures before, and also we discussed detailed about microwave ohmic heating as well as radio frequency heating. And so, this another 3 lectures we will be discussing about the advanced separation processes which are employed in the food industry. So, the first one we supposed to see is what is separation process, right, and few basics about this. Right. So, if any industry, the main aim is to process raw materials and convert them into products, right. So, this is my process. So, I have a raw materials, so which are converted into products, right. So, here my process requires my raw materials in some form. For example, so we take a size of raw materials, right. So, we need certain size of raw materials, or for example, we can say that if my size is too big, so the contact surface area will be very much small. So, for that case we will process the raw materials, the unit process is nothing but a size reduction. So, after size reduction I do not require certain size of the raw material, I need certain range of raw materials, right, range of size, right. So, in that case, so I would go for a separation process. Okay. So, from the separation process I will select the size range of the raw materials which will be further fed into process. So, in that case my separation is employed in the upstream of the process. And what happens in the downstream is, for example, if I take a plus B as a raw material and I will convert them into C plus D. So, this is my product. So, in the C plus D my interest would be on the D only, right, I would want only D. So, in that case also I will go for separation process to separate D from C, right. So, conventionally your separation can be from upstream side or from downstream side. So, based on the requirements, and sometimes what happens, this process itself a separation process, right. In most of the industries the separation process itself a main process. So, this is a unit operation in the sense where we do not involve any chemical reactions. The aim is just to separate solutes from solvents, or solute from a solute mixtures. Okay. So, for example, if we consider the waste treatment, wastewater treatment, where the membrane separation is also very much famous. So, there may be a 3 stages. The first stage would be coagulation or flocculation. the second stage would be of oxidation ponds. The third stage would be of membrane separation process. Okay. So, this way also the separation process can be done. So, the main process itself a separation process. So, there may be a series of stages. The first stage I would be doing it in using the coagulation technique. The second stage would be of oxidation pond. The third stage would be of membrane separation process. But in the food industry, where we are going to concentrate. So, the major process itself a membrane separation process. Membrane separation process. So, the example would be the clarification of juices. It is nothing but to get the clear juice solution, clarification of juices. So, this is little introduction about the membrane process. For example, how do I measure the separation, right? So, there is a parameter called alpha Ij, we call it as a separation factor. Okay. So, this is nothing but x1i upon x1j upon x2i x2j. So, this 1 and 2 are streams and I and j are species, right. So, when alpha ij is equal to 1, so then there is no separation at all. That is obvious, because the stream 1 have I upon j and stream 2 have I upon j. If it is 1, they both are equal. So, then we will not have any separation. So, if alpha ij, there may be a two situation, one is less than 1, another is greater than 1. If it is less than 1, the stream 1 is concentrated in J and 2 is concentrated in I. So, that means, so this is high and it is also high. So, that your denominator would be dominating. So, you will have alpha ij as less than 1. So, the greater than 1 is exactly opposite, stream 2 is concentrated in J and 1 is concentrated in I. Okay. So, this is the separation factor with which we can say whether the separation is possible or not, or which species in which stream is concentrated, right. So, then for the separation, so what is a requirement, right. So, for example, so this is a separation process. So, we send feed, right. So, the feed is converted into retentate and permeate, right. So, this both we call them as a product. So, this separation can be done using membrane as well. So, membrane separation as well, or if you take any common processes. So, you have a membrane separation process, you have a feed, you have a product. So, this separation to do, then I need to use some other external agency, right. So, how do I separate something from the feed as I wanted? So, that can be used, that can be done using energy or any material. Okay. So, for example, if you take the drying technology. So, in the drying technology, to remove the moisture or separate the moisture from the product, so what we are using is thermal energy. So, and for example, in food industries, another just we told the example is clarification of juice. Right. So, for that we use a coagulating agent. So, what it does is it forms the coagulation with the undissolved solids and that gets settled in the bottom, then your clear juice will be collected at the top, right. So, here the separation is done using a material. So, in the drying of food products, the removal of moisture from the feed is done using a thermal energy. So, to separate the desired product from the feed, so we need to use either energy or a material. And it is like the similar phenomena you might have studied in the chemistry, right. So, you use a catalyst to reduce the activation energy of the reactants. So, here also, so the energy or material whatever you use, right. So, that helps in exceeding the activation energy of the separation. Okay. So, this is my external agent, and also the separation works based on the two principle. So, one is the equilibrium governed operation, the second one is rate governed operation. Right. In the equilibrium governed operation, so the product phase as well as the feed phase are in equilibrium. In the rate governed operation, rate of the physical transport of species is responsible for the separation process. So, here in the equilibrium governed, both feed as well as product phases are very much important, right. The equilibrium governed we can say as a distillation, right. So, the rate governed or normal our membrane separation process, what is of our interest. Okay. So, this is the basic about the what is separation and what is the basic principle of separation, and what are all the major categories, equilibrium governed as well as rate governed. So, this is the basic about the separation process. So, we will see now the other things, what are all the fundamentals of separation process and what are all the advanced separation process, in that what we are going to concentrate. So, here is the fundamentals, the basics of separation processes used in the food industry. So, as I told earlier, in the food industry the process itself a separation processes. So, example is nothing but a clarification of juice. So, how it is being done? The plant carbohydrates, pectin, starch and proteins. So, these makes the colloidal suspension in the freshly extracted fruit juice. In the freshly extracted fruit juice, you will find all of them in the colloidal stage. So, we use the pectinol as a enzyme. So, as I told, it is a material we use for the separation. The pectinol enzyme is widely used for better juice recovery as well as the clarification of fruit juices. What it does is it breaks the pectin here and into soluble form, thereby freeing suspended particles which settle down and leaves the juice clear. So, if we add the freshly extracted fruit juice which contains pectin, if we add pectinol enzyme, so that clarifies the fruit juice. So, amylases are also used to remove protein as well as starch from the fruit juices. This is one example, and another example for the separation process which uses energy is home drying of vegetables and fruits. So, if we keep it for sun drying using the solar energy, the vegetables and fruits gets dried. So, that is using energy. So, here the separation process is done using a material, here the separation process is done using a energy. The equilibrium governed separation process or drying, as we just discussed. So, the water vapors from a solid material are removed using a vapor stream. So, here the vapor stream, the important parameters are temperature, relative humidity and thermophysical properties of the vapor stream, as well as the temperature, physical properties of the solid is also important when we are doing the drying. Drying is nothing but a equilibrium governed separation process. And the driving force for physical transport of species is generally a gradient of chemical potential. So, based on chemical potential gradient only the separation occurs here. The rate governed separation processes, example is membrane separation process. So, here the concentration gradient, pressure gradient, temperature gradient and electrochemical potential gradient are used as a driving force. So, the first separation process is nothing but a osmosis. So, first we will see the fundamental separation process, fundamental separation process. So, then we discuss about the advanced separation process. So, in the advanced separation process we are going to concentrate only on the membrane separation process. Okay. So, the osmosis is a basic separation process. So, this osmosis is observed when a solution is separated from the solvent by a semi permeable membrane. So, the semi permeable here in the sense it permits only the solvent. The difference in osmotic pressure across the membrane drives the transport of the solvent. The osmotic pressure is a colligative property. The colligative property means the properties of the solutions that depend on the ratio of the number of solute particles to the number of solvent molecules in the solution, but they are not depend on the nature of the chemical species. So, osmotic pressure here is a colligative property, that means it depends upon the number of solutes in the number of solvent molecules in the solution, and also it is a function of concentration. So, that is where we told in earlier lecture concentration gradient, pressure gradient as well. So, then the concentration gradient of the solvent is the main driving force in the osmosis. So, the solvent flows from the solvent side of to the solution side until the solvent activity becomes a almost equal in both the sides. Also, the hydrostatic pressure difference between two sides known as the osmotic pressure. So, for example, so I have a system where I employ a semi permeable membrane. So, initially both the side, the one side the solvent is there. So, another side there is a solution with solute molecules as well as solvent. So, after the separation happens, because the semi permeable membrane we told that it permits the solvent molecule to flow from the higher concentration to lower concentration. So, after some time what happens is, so we will see a solvent increase in the other side. Okay, so this side you will find less solvent. Okay, so this height is contributing to the pressure. So, that is what we call it as a hydrostatic pressure difference between two sides. So, this is H, so rho g H, right. So, this is nothing but a hydrostatic pressure difference between two sides, which is known as a osmotic pressure. If the initial concentration of the solute is more, in the solution side. So, that means solvent concentration is very low, then more solvent will flow in from the solvent side to equalize the solvent activity on both the sides, resulting in more osmotic pressure difference. So, that means if the initial concentration of solute is more in this side, then more solvent will be diffusing through the membrane. So, in that case this H will be higher than the case what we discussed. So, in that case, so you will have higher osmotic pressure difference. So, then another basic operation. So, this also we are going to see in detail about the advanced membrane separation process as well. So, here we will just see the basic definitions and what happens in the reverse osmosis. So, the pressure is applied on the solution side externally, so that the osmotic pressure is overcome and the solvents are forced out of the solution side. So, what we have done in the osmosis is, so from the solvent side the solvent moves to the solution side. So, here we are developing a osmotic pressure. So, now the externally the pressure is applied, so which has to overcome this osmotic pressure. If that is the case, then solvent back diffuses to the from the solution side to solvent side. So, that is what reverse osmosis is. Pressure is applied on the solution side externally, so that the osmotic pressure is overcome and the solvents are forced out of the solution side. The throughput of the process and the quality of the product depends upon the porosity, morphology and the thickness of the membrane what we are using in the reverse osmosis. The separation of lower molecular weight species is possible in the reverse osmosis. Mostly it is used in the desalination of water. Actually, the salt with a high osmotic pressure, the operating pressure in the feed side of the reverse osmosis process is extremely high, because they have a high osmotic pressure. To overcome that, we need to apply higher external pressure. In that case, the feed side operating pressure is extremely high in reverse osmosis. The deposition near the membrane surface leads to the concentration boundary layer. Once the membrane separation starts, the concentration of solutes gets built in the membrane surface. So, that further leads to concentration boundary layer. The next basic separation process is dialysis. So, here the two liquid streams are separated by a permeable membrane. A specific set of solutes from the feed side are permeated through the membrane to the dialysate side. Okay. So, here the permeation of solute is possible from the feed side to dialysate side. The transport here is affected by the concentration gradient between the two streams what we are using, and the rate of solutes through the membrane is a critical parameter in the dialysis. So, the example in the food industry is demineralization of milk. So, for that we use a dialysis operation. So, these are all basics, right. So, osmosis, reverse osmosis, and another is dialysis. So, these are all basic separation operations. So, in that still this reverse osmosis will come under the category of advanced. So, this is basic separation processes. Right. So, the advanced separation processes are, so all membrane processes. So, which includes RO, microfiltration and ultrafiltration and nanofiltration. So, all comes under the category of membrane separation processes. This is the advanced separation process. Dialysis, if it is done using the electrical input, then we call it as a electrodialysis. So, that also advanced electrodialysis. So, this also comes under the category of advanced separation process. Apart from that, there is another advanced separation process called chromatographic chromatographic separation process. So, these are all comes under the category of advanced separation process. Anyway, in the third lecture which talks about the electrodialysis, and also we are going to intensely concentrate about the all membrane separation process, RO, microfiltration, ultrafiltration as well as nanofiltration in terms of food industry, what is their use in the food industry. So, chromatographic separation I will just give the very brief introduction. Okay, so, the chromatographic separation. So, this is also called advanced separation processes. Okay. So, this can be done in many ways, for example, liquid chromatography, and gas chromatography, and gas liquid, and many variations are there. I will just introduce you about the liquid chromatography, what exactly happens. So, here how we separate the component is based on the mobile and stationary phase. Mobile and stationary phase. For example, my solvent is pumped, right, and sent to the chromatographic column. We call it as a column. This is chromatographic column. Okay. So, here the feed is injected in this line, feed. So, is injected in between the chromatographic column and solvent tank. So, then further it goes to detector. So, this detector normally we use UV visible spectrophotometer. Okay. So, this will give me absorbance versus time. To measure the absorbance, then I will discuss about the calibration curve. So, this is detector, and it further goes to the flow meter to measure the solvent flow rate. Okay. So, what happens here is the feed is injected in between. So, the feed normally a pulsed feed. So, which is about 1 milligrams per ml with the flow rate of around 1.5 ml per minute. So, the total volume handled would be around 10 microliter. Okay. So, then sometimes what happens, this chromatographic column itself kept in a oven to maintain the temperature, right. So, that also happens. The most common material used in the column is nothing but weak cation exchange membrane, weak cation exchange materials. Okay. So, the particle size is about 5 micron, and the pore size is about 100 Armstrong, and length is about 150 mm. So, then ID is around 4.6 mm. Okay. So, this is typical material which is used in the column. And also how it detects the component, right. The separation, how it happens is, so first we take a material, for example, in the feed contains more than one solute, right. So, each solute will come at different timings. So, for example, in x axis we have a time, so 1 minute, 2 minute, 3 minute, 4 minute. So, for example, the solute A shows up. So, this is a absorbance, right. So, the detector what you use is UV spectrophotometer. So, it measures the absorbance. So, I will take out here the solution, then go for at 1 minute various time intervals. For example, 1 minute, 2 minute, 3 minute, 4 minute. I will just take the sample here at this outside of the column, then I will go for the UV absorbance, and I will get a peak at 1 and 2 and sometimes 3 and 4. So, this is nothing but a different material, A, B, C, D material. So, that means, so at different intervals different materials comes out of the column. So, that is the way. So, the based on the mobility, then it gets a separation. So, how do we get the concentration of the solute from the absorbances? We supposed to do the calibration curve in the sense, for example, if I identify after 1 minute my A is showing up. So, A I will prepare various concentration, for example 0.1 milligrams per ml, then 0.2, 0.3, like that I will prepare. Then I will get the concentration versus absorbance. So, I will get the calibration curve. So, from that calibration curve I would be able to tell at 1 minute if my absorbance is this peak. So, how much is the concentration of A at 1 minute. So, after 2 minutes your A will not be showing up, your B will be showing up. So, at the time same calibration curve I will do it for B, concentration versus absorbance, and C also same thing. So, from this I will be able to know which time which material is coming out of the column and what is its concentration. So, from the calibration curve I will be able to detect my various components in the feed material. Okay. So, this is the basics about the chromatographic separation. Anyway, we are not going into detail about the chromatographic separation. We are only going to concentrate about the membrane separation processes, which are reverse osmosis, microfiltration, ultrafiltration, as well as nanofiltration, and also we will discuss about the electrodialysis. Okay. So, in the membrane separation process, the major usage is in dairy as well as beverage industry, and due to newer membrane materials and design, so this field is very much useful in the food industries, and also the concentration and fractionation are the two major areas of the interest in the membrane separation process. So, better quality products with minimum waste generation and higher energy efficiency would be the goal of the membrane separation process in food industry. For example, I used sterilization, I used a thermal energy, right, sterilization. So, I have done it whatever we have seen in last 10-15 lectures. So, the sterilization is done using a thermal energy, but here we use a filtration, the thermal energy. So, we are going to use the ultrafiltration technology, so which also filters the viruses, right. So, in that case I am not using a thermal energy which will also cook my product, right. The product gets thermally damaged if I do it using thermal energy, but in case of the microfiltration, so I can remove the viruses without heating the product. So, that means, so minimum waste generation as well as the quality of the product is enhanced. In the case of concentration, the membrane separation processes replace the thermal processes, resulting in energy efficiency. So, if you concentrate on the area of interest to concentration, so that is what I told. So, the thermal processes is replaced by the membrane separation process. In case of fractionation, membrane separation processes resulted in a minimum waste generation as well as the recycling of the byproduct is possible in the fractionation, but that is not possible if I use the thermal energy. For example, I am removing the moisture using the thermal energy, the moisture gets evaporated and it goes out of the system, but in case of the membrane separation process, whatever permeate or retentate you get, so based on your desired one, sometimes your retentate may be of desirable or sometimes your permeate will be of the desired product. So, based on the desired product, the undesired product can be recycled as a byproduct, but that I cannot do in the normal thermal processing. The cold sterilization of liquid food materials with improved shelf life and retention of flavor and nutrient is a major advantage of the membrane separation process, as I told. So, I will be retaining the flavor and nutrients in case of ultrafiltration. So, where my microorganisms gets removed, at the same time my flavor and nutrients of the food is retained. The application wise, the membrane separation process in food industry, water salination as well as purification, cold sterilization of beverages and recovery and fractionation of proteins from whey. So, this is very important application of membrane separation process in the food industry, and also the clarification of fruit juices, wines and beer, and removal of bacteria from water, and effluent treatment for removal of heavy metals, organic materials, separation of oil and water emulsions. This also used in food industry enormously. Removal of volatile organic components from the air. These are common applications, but these few applications are very much used in the food industry. So, then membrane operation mode and membrane materials. The size of the membrane pore is very much important. Based on that, we will have variety of membrane separation process. As I told earlier, microfiltration, ultrafiltration, reverse osmosis and nanofiltration. The microfiltration, the separation of macromolecules and particles that range in size from 1 to 10 micrometer, that is nothing but a microfiltration. The separation of macromolecules by a molecular mass, so that is generally from 5 to 500 kDa, kilodalton. So, that is nothing but a ultrafiltration. So, a membrane with the cut of 5 kDa, so that retains 90% of macromolecules with the molecular mass of 5 kDa. The ultrafiltration finds wider application in the whey protein concentration and fractionation, and reverse osmosis find applications in the desalination of water, and nanofiltration lies between the ultra and reverse osmosis. So, based on the application. So, the most common membranes used are polymers or inorganic materials. So, the cost of inorganic materials are very much high compared to polymeric materials due to their strength as well as the steam sterilability. And there are different modules with which the membrane separation process can be operated. One is hollow fiber module, spiral wound, plate and frame, as well as the tubular module. The spiral wound module has the highest specific area per unit volume, that is what we supposed want to get the retentate, and which has the limited application with the solution containing suspended particles, because it cannot be used for the solution which has suspended particles. The phenomenon of concentration polarization results in low acceptability of membrane technology in continuous process. This concentration polarization word is nothing but, so I have a membrane, so here the solute gets retented and the permeate moves out of the membrane. So, after certain time, so this retentate gets concentrated, so it forms another resistance for further flow of the feed through the membrane. So, that is nothing but a concentration polarization. So, the phenomenon of concentration polarization results in low acceptability of membrane technology in the continuous process, because in the batch process we know exactly the volume. So, based on that the membrane can be designed, but in the continuous flow it is the flow, the operation is continuous. So, since it is continuous, the concentration of retentate gets builded up in the membrane surface. So, that is very much unwanted. And the tangential filtration is carried out where flow of liquid is parallel to membrane. So, as we said earlier, so this is my membrane process. So where your feed is in here, so you will have the permeate. So, So, then you will also have retentate. Permeate is which passes through the membrane, retentate is what gets retained in the membrane. The filtration is carried out where the flow of feed is parallel to membrane. For example, so if you have a membrane module like this, so your flow of feed is also the same direction, the parallel to the membrane. This is a parallel line. The cross flow of permeate is perpendicular to the membrane surface. To improve the filtration rate, high cross flow velocity is maintained, and this results in reduced thickness of the concentration polarization layer. The cross flow is perpendicular to the membrane surface. So, there is a possibility for the concentration polarization, but if we maintain the high cross flow velocity, that can be avoided. The transmembrane pressure is the major driving force for the movement of solution across the membrane, and the concentration of solute increases, and this mass of solute is deposited on the membrane surface we just discussed. The concentration gradient on the feed side of the membrane with maximum concentration at the membrane surface. So, the maximum concentration happens at the membrane surface. And the solute cake or solute layer, solute cake in the sense in the case of membrane filtration, or solute layer in the case of ultrafiltration, results in higher membrane resistance and thus decline in the permeate flux across the membrane. So, that means the concentration polarization further acts as a resistance, and this decline in the permeate flux across the membrane. The flow of liquid is tangential to the membrane surface, and this flow attempts to reduce the thickness of the cake. This we discussed in the previous slide itself. The increase in solute concentration may also increase the viscosity, which may affect the transmembrane flux, and irreversible fouling of the membrane needs cleaning as well as the backflushing to restore the original flux. The fouling may be reduced by optimizing the process parameters, design parameters as well as the membrane materials. The fouling is nothing but the concentration of the retentate in the membrane surface, so which acts as a extra resistance for the permeate. The diffusion based membrane process, which is nothing but a pervaporation, where concentration difference across the membrane is the driving force. Here it is a transmembrane pressure for other membrane separation operation. The membrane separation operation is generally operated batch or continuous mode, both are possible. The batch, the volume of the solution decreases and the concentration of solute increases with the time. So, the solution gets processed and the concentration of solute increases with the time, but in the continuous mode the concentration of solute retentate remains constant. Then based on membrane material wise, the cellulose acetate and synthetic polymer membranes as well as the composite and ceramic membranes are available, and cellulose acetate membrane provides high permeate flux as well as it is easy to manufacture. It breaks down at higher temperature and sensitive to chemicals. So, that is the disadvantage of the cellulose acetate membrane. So, this is the older one. So, when the membrane separation processes were started, the cellulose acetate membranes were used. After the polymer area got picked up, then we moved slowly on to the synthetic polymer membranes. So, ultrafiltration polymer membranes made from polyamide, polyacrylonitrile, nylon as well as the polysulfones have been used for better chemical resistance, and ceramic or composite membranes made from carbon, zirconium oxide or alumina have the advantage of cleaning and sanitation due to their inert nature. So, this will not take place in the any reaction. So, due to their inert nature, so they are very much wanted, where your membrane should not react with the feed processed, right. Now, we are going to see about the different modules, tubular, hollow fiber membrane, plate and frame as well as the spiral wound module. The ceramic membranes are generally assembled in tubular modules, if the material is membrane material is ceramic. Easy replacement of membrane and cleaning of the membrane surface and no need for any costly pre-treatment of the feed is the advantage of tubular membranes. Tubular membranes are located inside the tube and the diameter is about 5 to 15 millimeter, and because of the size of the membrane surface, plugging of tubular membrane is not easy. This is a disadvantage, and packing density is low. Packing density is how much membranes you can pack in a single tube. So, which results in the high capital cost per module and high energy cost per unit of liquid treated, and low surface area per unit volume. So, packing density is also low and surface area per unit volume is also low. Necessity of high liquid flow rate to maintain the turbulence in the module, that is also disadvantage of the tubular membrane. So, the next one is hollow fiber. Anyway, we are having here. So, this is the tubular membrane. This is your tubes of 5 to 15 mm. So, here your feed is in. So, your permeate gets across the membrane and retentate will be retained and taken out, and the permeate comes out of the membrane and it gets collected in the tube module. Okay. So, the next one is hollow fiber membranes. A large number of small diameter fibers sealed at the ends with the epoxy resin, polyurethanes as well as the silicone rubber. The membranes are asymmetric in nature and the feed side having lower pore size and are self supporting. So, they have a very high specific area per unit volume. So, what are all the disadvantage of tubular membrane? So, that are taken care in the hollow fiber membrane and per unit volume compared with the tubular membrane. So, it is about 30,000 meter squared per meter cube, and clean solution and thus are most used in the gas separation or pervaporation. So, you can use this hollow fiber membrane when your solution is clean. So, in that case the most of the time it is used in the gas separation or pervaporation process, and hollow fiber membranes have low diameter, so that chances of plugging are very high compared to tubular membrane. So, this is your hollow fiber membrane. So, this is hollow fibers stacked together in the tube, and this is the flow direction, this is the tangential flow direction. So, the permeate is getting collected here and the retentate will be inside the membrane. So, this is the cross sectional view of hollow fiber membrane. So, this is the permeate gets collected. So, this is the concentrate gets collected in here. So, this is the single hollow fiber. So, feed is in the tangential flow. So, your permeate gets into the fiber that is getting collected, and this is nothing but a tube sheet, and concentrated will be taken out. Okay, so, then next one is plate and frame module. So, here also low specific area, which is also unattractive. In this module, two membranes are sandwiched with the feed sides facing each other. So, that means, so I have a membrane. Okay. So, this is the feed side of this membrane, this is the feed side of this membrane. So, feed side facing each other, it is stacked, right. So, that means the feed is going in between two. So, the permeate goes out of the membrane and retentate gets collected. So, then you will have here the feed side, then this is another membrane. Okay. So, this is the feed side facing each other. So, that means your feed retentate, this is an alternative module. The spacer is placed between the feed and permeate side, and to achieve the desired membrane area a number of sets are placed in parallel. So, this is equivalent to your plate and frame press which is used for filtration. So, this is based on the desired membrane area, these kind of modules can be connected together to achieve a particular desired membrane area. The membrane replacement and cleaning is easier because it comes with the separate modules. So, you can assemble deassemble them based on your requirement, and also cleaning is easy, it can be disassembled very easily, and no need for costly pretreatment of the feed, that is also advantage. And spiral wound module is an adaptation of plate and frame module. So, where membrane sets are wrapped around the central line. So, instead of keeping two membranes feed side facing each other, here we wrapped the membrane in the central line. So, compact structure with high pressure durability, and also it has the highest specific area among all the modules, but feed needs to be free of particles, that is disadvantage. So, we are going to see here, yeah. So, this is your plate and frame module. So, if you see these are all membranes. So, these are all membranes. So, the feed is entered here. So, you will collect the retentate here and the permeate is getting collected from the membrane module here. So, the feed as well as the retentate goes in the alternative compartments. So, this is nothing but a spiral wound. So, spiral wound, your membrane is wrapped in the central line. So, what happens is the feed is employed here, right. So, this permeate through the membrane. So, your permeate is getting collected inside the tube and your retentate will be in this side. Okay. So, this is nothing but a spiral wound membrane module. And types of membrane process, so as we discussed in the few slides before, the membrane is a selective barrier and this selectivity is important for separation. So, that means, so whether my membrane allows the solvent or solute or among the particular solute, alright. So, based on this selectivity, so we divide the membrane processes, and the various selectivity parameters used to influence the product concentration and removal of the solute from the solvent. So, one is diffusivity and size and shape of the particles, because when we were discussing about the different modules, we also told certain modules are not suitable for solution containing particles, right. Certain modules need only the clear solution, right. So, size and shape of the particle is also important, and electrostatic charge, for example, if you are using electrodialysis. So, this is important parameter to be considered, and physico-chemical interactions between the membrane as well as the feed. One of the module we also told the membranes are inert membranes, carbon or zirconium carbon. So, and the volatility will be taken care when we use the pervaporation process, and the solubility, right. So, these are all the selectivity parameters. And membrane materials, polysulfone, polyether sulfone and cellulose acetate, polyamides and polyacrylonitrile. So, these are all polymeric membranes, organic polymeric membranes. So, we also have the organic membranes, which is nothing but a borosilicate class, pyrolyzed carbon or zirconia carbon. So, these are also widely used. And the driving forces for membrane processes is concentration gradient, transmembrane pressure, chemical potential, osmotic pressure, electric field, osmotic pressure in reverse osmosis, then transmembrane pressure and concentration gradient, magnetic field, partial pressure. So, all of them are driving force based on the particular membrane separation process. So, the major categories are ultrafiltration, microfiltration and reverse osmosis. So, these are all classified as a on the basis of molecular size of the pores as well as the transmembrane pressure. So, here the major parameter or critical parameter based on which the classification is done is the molecular size of the pores as well as the transmembrane pressure. But if we see the pervaporation technique, which is based on the separation driven by the partial pressure. So, we have told here, right, the partial pressure and the selectivity that depends upon the solubility and diffusivity of species in the membrane, solubility as well as diffusivity of the species in the membrane. Okay, so, here I will stop this lecture. So, tomorrow we will see about the various membrane separation process. So, in the today's lecture we discussed about what is called separation process, where it exactly used in the food industry, and what are all the basic separation process and what are all the advanced separation process. Advanced separation process, the major ones are chromatographic and electric field assisted separation process as well as membrane separation. Chromatographic separation process we just discussed very briefly because we are not going to concentrate much on that, and membrane separation process as well as the electric field assisted separation process we are going to discuss in next to 2 lectures. So, membrane separation process, ultra, micro and nano filtration as well as reverse osmosis, and electric field assisted membrane separation process we will discuss about the electrodialysis, and if possible we will try to do few basic problems, and these are all the resources and additional references what I have used in this lecture. Thank you.